Okay, so for the volume, we've got two pieces here. We've got the cylinder and the cone. So for the cylinder, we start out with the area of the base, which is just the area of a circle. So that's pi times radius squared. So it'll be 10, not 20, which is 314 square inches. Then the volume, of course, is the area of the base times the height. So it's at 314 inches squared times the 30 inches, which is going to be 9,420 cubic inches. For part two then, the cone, the area of the base is still 314 inches squared. The volume, since that is a cone, is the area of the base times the height divided by 3. So the area of that base is 314 inches squared times the height of 24 inches divided by 3 is 2,512 cubic inches. We add those up to get 11,932 cubic inches is our volume. Any questions so far? Is that what you got? No? Did you see where you went wrong? Okay. Surface area. There are two pieces. Well, technically there's three pieces. One is the area of the base, which we've already found to be 314 inches squared. Two is going to be the lateral area of the cylinder, which is just that area that wraps around the cylinder. That is a rectangle, and for lateral area, I used to do LA with a little cylinder drawn next to it there. For lateral area, you need the perimeter of the base. The perimeter of the base, since it's a circle, is just the circumference of the circle, which will be pi times 20, which is going to be 62.8 inches. So the lateral area is the perimeter of the base times the height. Which is what, 5,024? No. 2,512, I believe. But let's double check it. My internal calculator is hiccuping today. Ooh, I missed that one by quite a ways. 1,884 inches squared is the lateral area. So that's piece 2. Piece 3 is the lateral area of the cone. Because the base isn't exposed, the top circle of that cylinder is not exposed, so that's not part of the surface area. Normally, if it was just the cylinder, we'd have to add the base in twice. This piece here would have to be added in twice because there's one on bottom and one on top, but it's covered here. The bottom of the cone is covered, so we don't need an area of the base for the cone. But the lateral area for the cone so do lateral area with a little cone by it, is the perimeter of the base times the S stands for slant height divided by 2 because this forms triangles now and not just rectangles. This was perimeter of the base times the height times just the height. Well, that was height because the sides of that cylinder went straight up and down, so the height was the length of the side. On the cone, the side goes at a slant. So the height of the cone is not the length of that side. So we have to find that slant length there. And we'll do that using this triangle here. On that triangle, this is 10, because the diameter is 20, so it's just the radius of that circle. And this is just the height here, 24, and that's a right angle. So that's 10 squared plus 24 squared equals s squared. If we solve that, you'd get s equals 26. That's going to be 100 plus 576. That's 676 equals s squared, and you square root it, gives you 26. So you've got 26 inches for that slant. So for the lateral area of the cone, we have the 62.8 inches of perimeter for the circumference of that circle, times 26 inches for the slant, divided by 2 because it is triangular shaped. Giving us 816.14 inches squared. So then we add those three. So we're going to, oops, 0.14, just 0.4, not 14. 816.4. So we're going to add 314 and the 1884 to that 816. We get 3014.4 inches squared. That is our total surface area. So now we've got a surface area in square inches, 3014. What if I asked for that in square feet? What would I do to that 3014.4? If I'm going to convert that, square inches are going to go on bottom, square feet on top. 1 square foot is how many square inches? It's 12 by 12, right? Which is 144. So is that 3014 divided by 144? 20.93 square feet. Our volume was 11,932 cubic inches. How would we change that into cubic feet? Twelve times 12 times 12, yes. So 1 cubic foot is 12 times 12 times 12, or 1,728 cubic inches. .91 cubic feet. So almost 12,000 cubic inches. Sounds like a lot, but it's really under 7 cubic feet. What do you think? A lot of people do struggle with the areas and surface areas and volumes just because of the visual aspect. Yep. The visual thing is something that develops between the ages like 6 and 10. You maybe don't know what to do with it, but that ability to visualize develops at that age. After that age, you can learn to cope with it, but you can never really learn to actually see it. You can train your brain to deal with, to kind of work around not being able to visualize it, but you really can never actually fully visualize it. So it's a tough topic to teach, because if you don't have the visualization, all you can really do is learn coping skills. Further review from last week. So if we have a shape like this, where one is an enlargement of the other, pretend those look the same. Those sides are actually straight. So one is an enlargement of the other. And we know it's an enlargement because I can tell you that these angles here are equal. And I'll tell you that they are an enlargement. So if I tell you that this side here is 8 inches and this one is 6 inches, and this side up here is 32 inches, this one over here is 9 inches. I want to find sides X and Y. Well, if it truly is an enlargement or reduction, the sides are what we call proportional. In other words, they've changed by the same factor. So we look for corresponding sides that we know the length of in both figures. And in this case, we have that pair. Which pair of sides is it? 8 and 6. They both represent this side right here. So we've got that relationship. 8 inches goes to 6 inches. Now let's say I want to find X first. Where does X have to go in this? Does it go with the 8 or the 6? It goes with the 6. It's from the same figure as the 6. So the 6 and the X both go on bottom because they're from the same figure. So what goes up here better be from the same figure as the 8. It also has to correspond to the X, which means it's going to be the 32 because that represents the same side as the X. So 32 goes up there. So you notice it has to have relationships in both directions. In this direction, those are from the same triangle, those are from the same triangle. In this direction, those are corresponding sides, those are corresponding sides, before and after the enlargement. So now we cross multiply. 6 times 32 divided by 8 gives us that X is 24 inches long. You do 8 times 4, you mean, to get 32? Then 6 times 4? You could do that, yes. So now to find Y, I still have that 8 over 6. Where does Y go with the 8 or the 6? That goes with the 8 because it's from the same triangle as the 8. So then what goes below it? The 9. And we will cross multiply and divide. 8 times 9 divided by 6 gives that Y is 12. What if I tell you the area of this figure over here is 720 square inches? And I want to find the area of this figure right here. Well, the ratio of lengths is 8 to 6. In fact, we could reduce that 4 to 3, correct? The areas, the ratio of areas is going to be found by squaring the ratio of lengths. 4 squared is 16, 3 squared is 9. So 16 to 9 is going to be the ratio of areas. The 720 square inches here, does that come from the same figure as the 8 or the 6? The 8, so that has to go on top. I'll put square inches on there so we know we get square inches down here. And we cross multiply and divide. So 9 times 720 divided by 16. 405 square inches. So the area of the smaller one's 405 square inches. That doesn't turn out too bad. I'm kind of impressed with my drawing skills there. These are similar figures. The small one is just a reduction of the large one. So we're going to say this went from 10 inches down to 6 inches. And I give you the volume of the big one here is Oh, let's say that it is 2,160 inches cubed. I want to find the volume of the little one. So I look at the lengths. My ratio of lengths is 10 inches to 6 inches. Can I reduce that? Yeah, 5 to 3, correct? My ratio of volumes, well, when I did my ratio of areas, what did I do to the ratio of lengths? Squared it. So for volumes, what do you think I'm going to do? Cube it to the third power. 5 to the third power is 5 times 5 times 5. That's 125. 3 to the third power, 3 times 3 times 3 is 27. That is my ratio of volumes. The 2,160 is from the larger figure. It's also from the figure with the 10, so that means it tells us it has to go on top. Cubic inches, so we will cross multiply and divide. So 27 times 2,160 divided by 125. 466.56 cubic inches. Does that look familiar? A little bit? Okay. So you can see these similar figures are very powerful. So then the next thing we want to look at is we want to start graphing. What graphing really is all about is there are a lot of cases where we have two numbers that go together. It might be looking at advertising dollars spent for a period and sales for the period. It might be height and weight. Might be hours studied and percent grade on a test. There are all sorts of things, all sorts of numbers that have relationships that come in pairs. So what we're going to do is we're going to list them as what's called an ordered pair. So let's say that a person who studies 6 hours a week gets 89% on the test. The first number always represents the same thing. In this case, it's hours studied. The second number also will always represent the same thing for these pairs, and in this case, that is percent grade on a test. The first one is sometimes called the predictor variable. The standard term for it is independent variable. Often called the X variable, because the letter X is what's most often used to represent it. The second one is called the dependent variable. Often referred to as the Y variable because Y is the variable most often used to represent it. So a little bit about those words independent and dependent. You got to be careful. It does not assume necessarily total causality, but it assumes a relationship. I mean, if you looked up somebody's grade on the test, you could assume they probably studied more, but getting a better grade didn't cause them to study more. Usually it's the other way around. Studying more causes you to have a better grade. You may have got the better grade because you studied more, but you're going backwards. The hours of studying has to happen first. Or you might look at height and weight. This is probably a better example Does changing your weight affect your height? No, I can put on weight anytime I want to. It's not going to make me taller. But does changing your height affect your weight? Yeah, if you get taller, usually you also get heavier. So it's kind of like I said, I don't want to imply that one does cause the other, but it's which one would happen first, which one would affect the other. Changing your height would affect the weight. Doesn't necessarily total causality because there's other factors. There might be one other, a third variable that causes both of them. Like getting older usually causes you to get taller. It usually also causes you to get heavier. So maybe it's getting older that causes both of them to happen. You can't necessarily assume causality. Same thing up here. Maybe studying more and getting a better grade are caused by something else. Maybe your mom calls you twice a day, nagging you to get your work done or do well in school. Well, that might cause you to study more and cause you to get better grades. Either way, we need to be able to represent pairs of numbers like this, where we need to not only indicate that the values, but that they go together and which one comes first. You know, if you recall, we graph numbers on a number line before. In fact, when we did our integers or positive and negative numbers, we used vectors to represent numbers. That would be the vector for 6, right? If we're looking to calculate with them, that's the best way to represent them. But if we're just looking to represent the value of 6, that vector could kind of clog up the graph in a hurry. So if we're just looking to represent values, putting a dot at 6 is the best way to represent it. We can't use it to do any calculations, but it represents the value. So if I have another one, you know, x equals 8, I can put a dot there. The number line, however, does not work great if I have a pair like 6, 8, implying that the 6 and the 8 are linked together, and that the 6 has to come first. You know, on the number line, I suppose I could do something like this, put an arc with an arrow indicating the 6 is first and then it goes to the 8. But you can see that would get very cluttered up if I had too many points on there. So a man by the name of Rene Descartes came up with the idea about 2,000 years ago. Let's take our regular number line, positives going to the right, negatives going to the left like we normally do, and we're going to name that the independent axis or the x-axis. And then we're going to do a second number line that goes through the 0 of this first number line, and instead of going horizontal, this one goes vertical. And the 0 of that number line is going to be on top of the first number line. So the two zeros are in the same spot. That spot where the two zeros are at is called the origin, because that's where both number lines come together. And on this one, we'll number positive going up and negative going down. So to plot that point, 6, 8. 6 is the first number. The first number is always the independent or the x-axis. So there's 6's right there. Notice I didn't make it very big because that's not really where our point's going to go. Then the y-axis is that vertical axis, or the dependent axis, it's often called. The 8 goes on that axis right there. Well, how do we show that they link together and that they're a single thing? Well, we project this out, we project this up, we put a single dot right there. That represents both of those values. Follow it down to the x-axis, it's a 6. Over to the y-axis, it's an 8. So that is 6, 8. So I might put a point like that. What would the coordinate of that point be? 2, 6, right? 2 down here, 6 up here. It's always this axis first and then this axis. We're naming the points. So we might have this point here. What would that one be called? -4, 2. Perfect. How about this one? Perfect. -1, -4. Good. So we can plot those points. Well, why do we care about plotting those points? Well, because we might have equations like these. (13 = 3x + 1). How did we solve that? Subtract the 1. Very good. 12 = 3x. Divide by 3. So 4 = x, or x = 4. Well, how is that different from this equation? It's a 7 instead of a 13, right? But when I go to solve it, what are my steps going to be? Exactly the same. I subtract 1 and then divide by 3. What about this equation? Same steps. You got it. Subtract the 1, divide by 3. So the reason the steps were the same was the right side of the equation, the side with the x, was the same in each equation. This is called a family of equations. In fact, there's an infinite number of equations I can write by having 3x + 1 on one side and then just changing the number on the left side. So I can represent that whole family simply by writing y = 3x + 1. That has an infinite number of solutions. No matter what number I pick for y, there's a value of x that makes it true. Or the other way around, no matter what value I pick for x, there's going to be a value of y that makes it true. So how do I represent those solutions? The solution to that? I can't list them out like this because there'd be an infinite number of them. I'd keep going forever and I'd still never list them all. So what I can do is I can turn it into a graph. To graph it, I have to figure out what those points are going to be on the graph. And to do that, I make a table. And what I'm going to do is I'm just going to pick values for x, and then I'm going to figure out what y has to be. So let's say, and I want to have values that kind of spread across the graph. So let's say I pick x to be -2. What would y be? Well, y would be 3 times -2 plus 1. What's 3 times -2? -6. -6 plus 1? -5, right? So that gives me the point x is -2, y is -5. So -2, -5, right there. Well, let's try x = 0. That's usually an easy one. So I put 0 in for x. Y will be 3 times 0 plus 1. What's 3 times 0? 0 plus 1? 1. So when x is 0, y is 1. So that point, here's 0. There's 1 right there. Well, let's try x = 2. So y would be 3 times 2 plus 1. What is 3 times 2? 6 plus 1? 7. So when x is 2, y is 7. So 2, 7. We see that that forms a line on our graph. Not always quite that simple. We might have y = x² minus x minus 2. Actually, let's make it a little simpler to graph. Minus 2x minus 3. That'll be a little simpler. So if I make a table here and I pick values for x, let's start out with x equals negative 2 again and figure out what y has to be. Well, y is going to be negative 2 squared minus 2 times negative 2 minus 3. I just replaced x with negative 2. Now here's where you got to be careful. Your calculator often wants to tell you the wrong numbers here. Negative 2 squared is positive 4. Negative 2 times negative 2, also positive 4. 4 plus 4, 8 minus 3 is 5. So it's at negative 2, 5. So negative 2, 5 is right there. Let's try x equals 0. We've got 0 squared minus 2 times 0 minus 3. What is 0 squared? 0. Negative 2 times 0? 0. Well, 0 plus 0 is 0 minus 3? Negative 3. So when x is 0, y is negative 3. So 0, negative 3 is right there. Let's try x is positive 2. That's going to be 2 squared minus 2 times 2 minus 3. What is 2 squared? That would be 4. Negative 2 times 2? Minus 4 minus 3. What is 4 minus 4? 0 minus 3 is negative 3. So at positive 2, y is negative 3. So positive 2, negative 3, right about there. Well, it's pretty obvious this is not a straight line. Those 3 points, however, are not nearly enough to tell us what this looks like. But what they do is they tell us where we want to look further. For example, I might want to know what happens in between these points, somewhere in here. So that would be x equals 1, right? I might want to find out what happens over here. So it might be x equals 3 or 4. Let's do that. Let's do x equals 1 and x equals 3. See what that does for us. So at x equals 1, y is 1 squared minus 2 times 1 minus 3. What is 1 squared? 1 negative 2 times 1? Negative 2. What's 1 minus 2? Negative 1. Negative 1 minus 3? Negative 4. So at 1, we're at negative 4. So 1 and negative 4 is right here. So that's not bad. Tells us that's probably where we turn around and head back the other way, right? So let's do x equals 3. So then y would be 3 squared minus 2 times 3 minus 3. What's 3 squared? 3 squared, you think cubed? 9. Negative 3 times 3? Or negative 2 times 3 is negative 6. Minus 3. What's 9 minus 6? 3. 3 minus 3? 0. So when x is 3, y is 0. That gives us a point right there. Well, what we can see is going on here, and you may want to do more points. You might want to do a point here where x is negative 1. That would be negative 1, 0, by the way. And maybe you want to do a point up here at x equals 4. It would be 4, 5. That would make it very clear. That looks something like that. It's called a parabola. So when you're plotting these points, that's kind of the key is you plot a few points to kind of get a feel for the graph. Then you look at the graph and figure out where you need more points to figure out how it looks. So what I've got for you, I want you to take some time to work on. It's a worksheet on graphing that I'm going to hand out to you. It's got several of these examples. Normally I'd have you partner up, but So let's just take a look at how these ended up. Oh, now it fixed them all of a sudden for some reason. Huh, weird. Anyway, number one here should look like this. Nice straight line. Second one will look something like this. Oops, I got something off there. Let me try that again. There we go. Looks like that. What do these mean? Well, these are all the solutions to either of those equations. Any point on here, even if it's not part of the table, like here, if I just take a point right there, that's x equals 1.5, y equals 3. 1.5 comma 3 would be a solution. If I put 1.5 in there for x, I should get 3 for y. Something's a little bit off there, but actually it's it wouldn't be 1.53, it'd be 1.5, 2.5. I just traced it wrong on my graph. So that would be a solution to that equation. Every point on there, like this point here, right here, that is 2.5 for x and 3.5 for y. 2.5 comma 3.5. If I put 2.5 in for x, y should be 3.5. Every point on either of those is a solution to that equation, the equation it goes with. So I'm going to have you try these two. I did suggest some points here, especially on this one. Try to use the ones I gave you. Again, I'll give you a couple minutes. Let's take our break first, and then we'll come back at like 9. So let's take a peek here. So number 3 here, y equals x squared plus 2x plus 1. It's going to look something like that. Number 4, y equals the square root of x plus 6. It's going to look something like that. You'll notice on all the other ones, I put an arrow on both ends of them. But on number 4, I did not. I only put an arrow on this end. This end's just a dot. The reason for that is I can't keep going in that direction. If I made x -7, if I put -7 in here, well, -7 plus 6 is a -1, and I can't take the square root of a negative number. So if x is smaller than -6, I'm taking the square root of a negative number. That doesn't work. That's called, the technical term of this, were a more formal algebra class, like an intermediate algebra class instead of a pre-algebra. That would be called a limit on the domain. It limits the values of x. I'm going to have you try these two. I'll give you. So number 5 isn't so bad. What'd you get from number 5? What's that? Almost done with it? Looks something like that. Okay, that's what it should look like. If x is -2, y is 3 times -2 is -6. 3 plus -6 is a -3. So -2, -3 would be right there. Don't know why my line doesn't want to stay there. Better, dang it. If x were -1, 3 times -1 is -3. 3 plus -3 is 0. So that's -1, 0. If x is 0, 3 times 0 is 0. 3 plus 0 is 3. So 0, 3 is right there. So that gives that line. Need a little more time for number 6? Okay. You just graphed them backwards? Okay. I'll give you a couple minutes on number 6 yet. So number 6. Looks like that. -2 gives you like 0.1, 0.25. -1 gives you 0.5. 0 gives you 1. 1 gives you 2. 2 gives you 4. That's called an exponential curve, by the way. You'll notice, by the way, that no matter how far you go negative here, the value of y never reaches zero. It gets smaller and smaller, but never reaches zero. That's something called an asymptote. Let's try 7 and 8 here. 7 isn't so bad if you're careful with it. Kind of an S curve like that. That's similar to what you got. It's really easy to mistake that one as a straight line, but it's not quite. Yeah, so this is, -9, -2, -1, 0, and 7, something like that. Anything for number 8? I'll let you off the hook. That's a -1, yep. That's -2. That should be -4, right? Oops, that'd be -8, never mind. -8 would be right there. If I put in -2, I'd get -4. Gives me a curve, something like that. I put in the 1, I've got 8. I put in the 2, I've got 4. The 8, I've got 1. If I put in 4, I would have 2. Oops, like that. I get 2 separate curves. Remember, we talked about those asymptotes up in number 6. There's another asymptote here, this one right here. It's an asymptote and it's a limit on the domain like we had in number 4 with the square root. X cannot equal 0. Because if x were 0, we'd be dividing by 0. So it's a limit on our domain. It's also an asymptote because the line here will get closer and closer to that, but it'll never touch it. There's also an asymptote here. That gets closer and closer to 0, but never touches it. Same here. That's a weird one to graph. 2 more for you to try, and then we'll sum this up. Number 9 here is a little bit tricky. If your graph at 0 ends up being -8, 1 ends up being -4, and you get something very narrow like that. Again, it's a parabola, kind of a U-shaped, V-shaped type deal. Number 10 should be a line. Look something like this. So before we leave here, there's the last thing I want to point out. There are 4 of these that form lines. 10, 5, 1, and 2. So if we look at the equations here that formed lines and the ones that didn't. We'll wait for the system to come back on. So we had the first two, y equals 3x minus 2 and 6 minus x. If it comes up here soon. There it is. Then we had y equals x squared plus 2x. Plus 1 was not a line. Y equals the square root of x plus 6 was not a line. Y equals 3 plus 3x was a line. Y equals 2 to the power of x was not a line. Y equals x to the third minus 1 was not a line. Y equals 8 over x was not a line. y equals 4x squared minus 8 was not a line. Y equals 3/4 x minus 4 was a line. As we look at these, what do you see that's different between the ones that don't make lines and the ones that do make lines? Okay, the same numbers. That's just because I got stuck on 3s and 4s for some reason when I was doing these. Exponents. In fact, two different types of exponents. One is a power on the variable, on x in this case. The other one would be this one here, x being in the power. This is actually a power on x. Square root we thought of as a power of 1/2. So that's actually a power on x. The last thing is this one right here. What's going on there? Divide by x. These three things right here, three things, if any of those three things appear in the equation is not going to make a line. So that's step one, is to identify whether the equation is a line or not. On Wednesday, we'll look at step two, which is finding shortcuts for graphing lines. For right now, there is a new quiz. It is due tomorrow, Tuesday, at 11:59 p.m. And there is a new homework due for Wednesday.